Hi folks, welcome back to Physics with Captain Rod. Making this video here to describe just conceptually a little bit about electric power generation. So what I'm going to use here is this University of Colorado simulation here. And congrats on writing these things. These things are great. So this thing just gives you kind of an idea of how electrical power is generated. For starters, you have to have some sort of mechanical energy source. In this case here, we have running water. And the running water turns this magnet. And what's happening over here now, let me stop that for a minute and put field lines in it. So as this magnet rotates around, I'm going to leave it right here for a moment. Notice here we got the south end of the magnet. The field lines run north to south, so these magnetic field lines go like so. In fact, can I move this compass? Yeah. Whoops. This thing's giving me a little trouble. But if I put the compass kind of interior of the magnet or close enough, you'll notice that the magnetic field lines, they're pointing right to left. Now, a little bit of a review here. Remember that Faraday's law of induction is linked on the concept of magnetic flux. So magnetic flux occurs when you have any sort of area here, and I drew some green lines in the area, with a magnetic field in that region. You take the component of the magnetic field that makes a right angle to the area and multiply them, and you get a quantity called magnetic flux. So in this picture, it would be magnitude of the field area times cosine of the angle between this normal vector and the magnetic field. Now, Faraday's law of induction basically states that anytime you change your magnetic flux, you're going to get an induced, whoops, let's use a different color here, you're going to get a voltage induced in that loop. And that voltage, at least to within polarity, is equal to change in magnetic flux over change in time. So changing magnetic flux always results in a voltage. Now, look at this equation-wise. The flux is equal to field strength times area times the cosine of the angle between the magnetic field and the normal here. You can change your flux by either changing B, or changing A, or changing the orientation. So as we look at this loop right here, we've got a magnetic flux in this region. You notice the magnetic field vectors are pointing basically right to left. See if I can get that thing right in the loop there. But as that magnet goes around and changes, you see how the direction of the magnetic field is changing, and therefore the flux is changing. At the orientation shown, the flux here is approximately 0. Now the flux is increasing. Now the flux is some maximum value. And now decreasing. Right. At this orientation, the flux is approximately 0. Maybe not exactly 0, but approximately. And you can see that as the magnet goes round and round and round, we are constantly putting a voltage on this. Now you'll notice that the voltage, half the time it's in one direction, half the time it's in the other. Well, that's because if I just did a quick sketch, and I'm going to make this real quick, if we were to sketch how the magnetic flux is changing against time, and you must realize that, see how this thing's spinning here. Half the time the flux is coming from the left, half the time from the right. So if we define, say, flux from the right as positive, this graph might look something like this. Whoops, I'm having some trouble with my pad here. I'm going to put this graph down here. So the magnetic flux would look something like this. And it's not important whether it starts here or here, by the way. Now, that means that the induced voltage, and I'm only going to worry about polarity here right now. I'm sorry, I'm not going to worry about polarity is what I meant. So the induced voltage, by the way, you'll notice here the slope is positive. You're getting, in fact, it's the largest it is in the entire curve. So the voltage at that point is a maximum, and the slope here is 0. And here the voltage is a maximum, but in the other direction. And here the slope is 0. So your voltage curve looks, kind of something like this. So again, I'll make other videos about the relationship between the voltage and the magnetic flux. Actually, when you write out Faraday's law of induction, It's actually that the induced voltage is minus delta phi over delta t. That has to do with Lenz's law. This actual curve is actually upside down, but not important for this discussion. What is important here is how the power generation works. So let's get back to this. You have some sort of mechanical input. In the simulation here, this is water, gravitational potential energy, basically, rotating the magnets, producing changing magnetic flux here. In an actual power plant, the energy source, right, rather than the falling water, well, it could actually be falling water if it was a hydroelectric plant, but the energy source is more typically maybe combustion of a fossil fuel like coal or natural gas or whatnot. We don't burn, I don't think, a ton of coal here in America anymore for electrical power, but I know in China right now they're burning a ton. Nuclear fission is a real common one as well, where uranium atoms are split into lighter atoms, releasing lots of energy in the process, basically turning water into steam to turn turbines. Right? What would be another one? Wind power. Wind power would be producing the input energy here to turn a turbine and produce the electrical energy and so forth. Now while I'm at it, and I'm going to skip the math here. I'm just going to kind of write this down equation-wise. I'll go through the math in another video. So the voltage induced, you'll notice that we're getting some sort of sine wave. Now I notice that mine starts at 0, 1, and one could say it's a cosine wave. Well, the starting point never matters. I could just as easily started this at 0, 0, 0. I'm sorry, at 0, 0. So the voltage has a sinusoidal pattern to it. So it's going to equal some maximum voltage times the sine of omega t, where this omega here is your angular frequency in radians per second. The V max is whatever your maximum possible voltage is. Now, when we think about what's happening here in the changing magnetic flux stuff, you notice that the area of the loop isn't changing. The magnetic field strength, well, one could argue it's kind of changing, but basically what we're doing here is we're changing the angle between the magnetic fields and the in this area. And in a real schematic of a power generation, that's the one that you're actually changing here, is this one. So the maximum voltage depends on, let's see, I'll put is a function of your field strength. It's a function of the number of turns in the loop, and it's a function of the angular velocity, how fast the loops are rotating. So typically what we get is that this voltage, the input voltage, is equal to N times B times A times omega times the sine of omega t, where this product right here, the product of the number of loops, the field strength, the area, and the angular rotation rate yields the maximum voltage. So I think I'm going to just leave that right here, this video. I'll make other ones about the equations and getting a little bit more detailed. I just wanted to kind of conceptually talk about how electrical power is generated. Quick little review of that. One, it is hinged on the idea of changing magnetic flux in Faraday's law of induction. Two, you have to have some sort of mechanical energy input to turn turbines. Three, that mechanical energy input usually is, I'd say nuclear fission is probably a pretty common one, or the combustion of some sort of fossil fuel. Again, both of those are used to create heat, turn water into steam, and turn turbines. Hydroelectric is another common one, and also wind power. So, and again, this is a conversion process. Some sort of energy input is being converted to electrical. Mankind doesn't have the ability to create electrical energy. What power plants do is convert energy from one form to another. So again, just meant to be a conceptual video. I think I'll just leave it off there. Have a great day.